Hi everyone, my name is Rahab Qasim, and today I'll be proving that E is irrational. So before I begin my proof, I just want to start with a brief history of E. So E is a mathematical constant and it's used to describe growth and rate of change. E is equal to 2.71828182845, and it just keeps going on and on and on to infinity. It's an irrational number. It was first discovered by Jacob Bernoulli in the 17th century, and he discovered it while he was studying compound interest. But it was Euler later on who discovered the exact constant up to 23 decimal places. So Bernoulli knew that it was somewhere between 2 and 3, but it was Euler who found the exact constant up to 23 decimal places, and it was Euler who called it E. And then later on, other people ended up calling it Euler's number. So I'll begin my proof now. I'm going to prove this using contradiction. So to begin our proof, we will first assume that E is rational because we want to prove this by contradiction. Therefore, E is equal to P over Q, where P and Q are elements of the integers, and Q is not equal to 0. Now, E has an infinite series expansion, and that is E is equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and that just keeps going on and on and on to infinity. So what we're going to do here is we will call this equation over here, equation 1, and we'll call the infinite series expansion of E equation number 2. So what we're going to do is we're going to multiply equation 2 by Q factorial. So then on the left-hand side, we'll have Q factorial times E, and then on the right-hand side, we'll have Q factorial plus Q factorial over 1 factorial plus Q factorial over 2 factorial plus Q factorial over 3 factorial, and that goes on and on and on to infinity. Okay, now what we're going to do is we are going to rewrite Q factorial as Q times Q minus 1 factorial. So if you look over here on the right, I'll circle this right here. So we know, just to explain what I did there in case it doesn't make sense, so we know that 5 factorial is equal to 5 times 4 times 3 times 2 times 1. Well, another way of saying that, or another way of writing that, is just that 5 factorial is equal to 5 times 4 factorial. So that's what we did here with Q factorial. Okay, so Q factorial is equal to Q times Q minus 1 factorial. So what we're going to do is we are going to replace, so back to our equation here, this one right here. What we're going to do is we're going to replace the Q factorial with this, okay? So Q factorial times E is equal to Q times Q minus 1 factorial times E. So that's the left-hand side of the equation. Now, if you remember when we said that E is rational, we have this equation right here, E is equal to P over Q. Well, if we multiply both sides of the equation by Q, we get E times Q is equal to P. And then if you look over here, well, here we have an E and here we have a Q. So what we can do is we can replace the E, substitute the E in E times Q with a P. Okay? So what we did is we took Q factorial times E, and then we changed that to P times Q minus 1 factorial. Okay, so we know that P is an integer, right? Because in the beginning we said that E is rational. It can be written as P over Q, where P and Q are both integers. So we know that P is an integer, and we also know that Q minus 1 factorial is an integer because Q is an integer, 1 is an integer, therefore Q minus 1 factorial is an integer, and then an integer times an integer is an integer. So the left-hand side of our equation is an integer. So one thing that I wanted to point out was when we look at our equation where we multiplied e by q factorial, on the right-hand side of the equation, remember we'll get q factorial plus q factorial over 1 factorial, and then eventually we're going to hit the qth term, which is going to be q factorial over q factorial. And then after that, we'll have q factorial over q plus 1 factorial, because q is an integer. So looking at this equation, we've already shown that the left-hand side is an integer. So if we look at the right-hand side and we look at each of these terms individually, well, we know that q factorial is an integer. We also know that q factorial over 1 factorial is an integer. Now, when it comes to q factorial over 2 factorial, well, this is also an integer because eventually what's going to happen in the numerator, q factorial is going to get down to 2 factorial, and then the 2 factorial in the denominator is going to cancel out with the 2 factorial in the numerator. So that is an integer. Same with q factorial over 3 factorial, all the way up until the qth term, and obviously q factorial over q factorial, that's just 1. Those are all going to be integers. So what we need to find out now is we need to figure out the rest of this equation, whether these are integers or not. And they should be integers because the left-hand side of our equation is an integer. So the right-hand side of the equation should be an integer as well. So if all of these are integers, the rest should be integers as well. But we need to show that. So we're going to call the rest r. And we're going to write it down over here. So r is equal to q factorial times 1 over q plus 1 factorial plus 1 over q plus 2 factorial plus 1 over q plus 3 factorial. So what I did here is I factored out q factorial from the numerator, and then what I'm going to do next is I'm going to multiply that q factorial back in. So let me show you this on the side. So q factorial over q plus 1 factorial. This is equal to q factorial over q plus 1 times q factorial. So the q factorial and the q factorial cancel out, and then you're just left with 1 over q plus 1. So that's what I did here. So then you're going to get 1 over q plus 1 plus 1 over q plus 1 times q plus 2 plus 1 over q plus 1 times q plus 2 times q plus 3, and that will go on and on and on to infinity. So what I'm going to do next is I'm going to factor out 1 over q plus 1 from the equation. So then I'll be left with 1 over q plus 1 times 1 over q plus 2 plus 1 over q plus 2 times q plus 3 plus 1 over q plus 2 times q plus 3 times q plus 4. Okay, so I noticed that I made a little mistake over here, so let me fix that. There should be a 1 over here, okay? Okay, so now if we look at this equation, we know that this equation is less than the equation underneath it. So 1 over q plus 1 and 1 over q plus 1, they're the same. 1 and 1 are the same. But if we look at here, 1 over q plus 2 and 1 over q plus 1. Let's say q is 2, for example. So 1 over 2 plus 2, 1/4 is less than 1/3. So, and then the same thing for the next term. So 1 over q plus 2 times 1 over q plus 3, that's going to be less than 1 over q plus 1 squared. So going on and on and on, as this goes on to infinity and that goes on to infinity, this equation will always be greater than that equation. So in order to continue with our proof, we need to have a short mini proof here. And this mini proof is going to show that if x is less than 1, the sum of n terms is equal to 1 plus x plus x squared plus x cubed plus x to the n. So what we're going to do is we're going to multiply both sides of this equation by x. So you're going to get x times s to the n is equal to x plus x squared plus x cubed plus, eventually we're going to get x to the n plus x to the n plus 1. So what we're going to do now is we're going to subtract x times s of n from s of n. So I'll show you what we're going to do here. So we're going to subtract this second here. We'll call this number 1 and we'll call this number 2. So we're going to subtract the second equation from the first equation. So what's going to happen is the x and the x are going to cancel out, the x squared and the x squared are going to cancel out, the x cubed and the x cubed are going to cancel out, x to the n and x to the n are going to cancel out, and you're going to be left with 1 minus x to the n plus 1. Okay? Now here on the right-hand side, I just factored out s of n, and so I have s of n times 1 minus x is equal to 1 minus x to the n plus 1. So the problem is that this was a finite sum and our equation E is infinite. So when we look at this, we have to evaluate what happens when n goes to infinity. And as you can see, so don't forget x is less than 1. So if x is like 1/2, so 1/2 times 1/2 times 1/2 times 1/2, eventually it just gets smaller and smaller and approaches 0. So as n approaches infinity, x to the power n plus 1 approaches 0. So basically on the right-hand side, we end up getting 1 minus 0 right here, because x to the power n plus 1 approaches 0 as n goes to infinity. And then what I did here was I divided both sides of the equation by 1 minus x, and that left me with this equation. S of infinity is equal to 1 over 1 minus x. So that's what happens to a sum when x is less than 1 as it goes to infinity. And the way this relates to our equation E is our x is basically going to be 1 over q plus 1. So here we have x is equal to 1 over q plus 1. So what we're going to do is we're going to plug this x, 1 over q plus 1, we're going to substitute it into x in this equation. So what we're going to get is s of infinity equals 1 over 1 minus 1 over q plus 1. And then basic arithmetic will give us q plus 1 over q. So s of infinity is equal to q plus 1 over q. So if we go back and look at our inequality, we have r is less than 1 over q plus 1 multiplied by this infinite sum right here. And we've already shown that this infinite sum is equal to q plus 1 over q. So r is less than 1 over q plus 1 times q plus 1 over q. So what we're going to do is we are going to cross these out. We're going to multiply this and cross these out. So then that will give us that r is less than 1 over q. Okay? Now, we also know that r must be positive. So r has to be greater than 0 because it is a sum of positive terms. Okay? So that means that r has to be between 0 and 1 over q. Now, we also know that 1 over q is less than 1. So that means that r has to be less than 1 and greater than 0. So if we look back at our equation here, we were trying to show that this one here, we were trying to show that we've already shown that the left-hand side was an integer, and we were trying to show that the right-hand side was an integer. So we were able to show that everything was an integer up until r. And now we've shown that r can't be an integer because r has to be an integer that is greater than 0 and less than 1. And there's no integer that is greater than 0 and less than 1. Therefore, we have a contradiction. And since we have a contradiction, that means that E cannot be represented as a rational number, and that means that E is irrational. Thank you.